Okay, so here's our last case, when c is less than 0. So we're basically going to establish the same type of proof as before, except we have to be a little bit more careful with c simply because it's negative. So if you take a look here, notice that we can state once again that the difference between the upper and lower sums of our function is less than epsilon over, in this case, the absolute value of c. That way this inequality holds true, since the absolute value of c will now become positive. So by definition, originally we knew that capital Mi really represented our supremum of our function, and lowercase mi represented the infimum of our function upon some domain. But now what's going to happen is if we rewrite this inequality and replace f of x with c times f of x by multiplying everything by c, our inequality symbols will actually turn direction, and now c times capital Mi becomes our infimum, and c times lowercase mi becomes our supremum of our function c times f of x, based on the fact that c is less than 0. So now if we look at our upper sum, it's written a little differently. C times the series sum of lowercase mi, and our lower sum will hold the same properties as being written as c times the series sum of uppercase mi. So now when we establish the same relationship as we did before, looking at what happens when we take the difference between the upper and lower sums of c times f of x, we now replace with the series sums and once again can factor out our c. However, if you look inside the parentheses, we have lowercase minus uppercase mi. So that's going to be a problem in establishing the difference between the upper and lower sums of f of x. But if we multiply both outside and inside by -1, and we can rewrite that looking the way you see here, by replacing c with its absolute value to switch its sign, and changing the direction of what's inside our parentheses for our series sums, now we can see that this looks very similar to the difference between the upper and lower sum of our original function f of x. So let's once again go ahead and replace the right-hand side with e divided by the absolute value of c. And here you can see our absolute values of c will cancel, leaving us with just epsilon. So now coming back to our function, we can now say that the difference between the upper and lower sums of c times the function f of x is less than epsilon. And by definition, that must mean that c times f of x is integrable upon the closed interval ab when c is also less than 0. So what this tells us now that we've proven for all cases is that now that our results have been validated, we can say the following is true. If our function is integrable on some closed interval ab, then for all real numbers, any scaled version of that function will also be integrable upon that domain. Thanks. Have a great day.